So the next concept is the body effect. Okay, so the body is the substrate on which the CMOS devices are built, correct? Normally, we are assuming that the biasing level of the substrate, right, is equal. Normally, every body of a transistor that is used in a circuit, sorry, and the body effect is the case where normally we expect the substrate of each transistor in a circuit is expected to be at the same biasing level, right? So the bias level of each substrate, okay, should be same. This is what we expect, right? But you see what happens when we use the transistors, right, when they are connected one after the other, right, vertically. So normally all the MOS transistors are connected in one after the other, maybe in a vertical fashion, right? Yeah. Consider the vertical stack of NMOS devices as shown below, right? So that is, this is one NMOS. Let me assume that I have another NMOS. Maybe this is grounded for the time being, right? So we also know that this is the gate of the first transistor. Maybe this is the gate of the second transistor. All right. Now we actually show that there is a body of the transistor like this. So when you put an arrow mark over here, right, this indicates it is the connection of the body. Okay. Yeah. Right. Normally what you do, this is the body or the substrate. I'll just write substrate over here, right? So this connection is also going to be a substrate, right? In a NMOS, we know that this is a body of the transistor and this will be the source of this, right? This is the source terminal. This is the drain terminal, source and the gate. So here this is the drain, gate and the source. So we know that substrate, that is a body, and this are shorted. So I can write this is voltage S and body. So this is also the voltage S and the body. If I call this is a transistor 1, I'll call VSB1 is equal to 0. VSB2 is also equal to 0. Right? Assume that I apply at least V threshold, right? And V threshold here so that both the transistors are turned on. Okay, fine. Now you tell me what is, see, it says that there is no difference between these two, correct? SB is equal to 0, but my question is what is VS and what is VB? Is it 0 or it's any other voltage? Yeah, VG will be a some voltage which is equal to VTH, that is threshold voltage, that is. So at this point you have some voltage, correct? At this point you have a voltage. That voltage is shorted to substrate, correct? So because of that reason, right, I know that, right, even when I short it, right, it's not equal to 0. So the VSB is, right, VSB1 will become equal to 0 because it is connected to ground. Here I have 0 volts, right? So substrate is also at 0 volts. But now you see that since this is a different voltage than 0, it is not ground, right? This point is not ground. So not 0. The second S, right? The second MOS transistors source is not at ground. So because of that reason, even the substrate is not grounded. So you have a different voltage coming into picture, right? The variation of, right, these voltages are different, right? When then the working of this transistor is definitely different compared to this. So this particular situation is called as the body effect. So variation of the threshold voltage due to the source to substrate voltage is called as the body effect. Are you okay? Source to the, yes, right? Only that is a definition required here. Okay. So the variation of the VTH, which is the threshold voltage, due to the source to body, or it's also called as substrate, source to body or source to substrate voltage is called as the body effect. So variation of the depletion charge content varies because of this threshold voltage, correct? So under the oxide layer will definitely change when you change this value. So because of which you have change in the VTH. So how the VTH varies, we'll write an equation now. Okay. So this VTH is equal to root of 2 times Q into Na times epsilon of silicon whole divided by oxide layer capacitance into root of this is 2 times phi s plus VSB minus this is root of 2 times phi s. So same equation you can find even in many of the books. All right. That might not come. Usually the problems are not asked on this, but if they ask a question, you have to answer, right, in terms of the diagram. And yeah, correct. Okay, then the next effect is called as the drain punch through. It's called as a drain punch through effect. Now let us assume that you are going to apply a very high voltage to the drain terminal of the MOSFET, right? It means the depletion region around the drain will completely occupy the channel and even, right, extend to the source, right? Which means the current will start to flow because the drain region has expanded and reached till the source, right? Which means drain and the source are connected by a huge amount of what you call space, right, through the depletion layer, and that will cause a current to flow irrespective of the gate voltage, right? That is called as drain punch through, right? If you apply a huge voltage to drain, right, the reverse bias causes the depletion layer to increase. This depletion layer could increase to a very large extent if you apply a very huge voltage to the drain, right? So the depletion region may extend in such a way that it will overlap with that of the source region, which means, right, the drain has a depletion, source also has the same depletion, which means it's the same region, correct? When you have the same region, you don't have to wait for any channel, so there is no requirement of gate region. Directly a very huge current will flow. That will damage your device because a huge current will flow, not the required amount of current, right? You are actually making the connection, right, in a wrong way. connection between drain and source, you are trying to build that connection not by building a channel, by connecting the depletion layers. There is a difference, correct? So because of this, the effect is called as drain punch through. All right, a huge current will start flowing over there, right, uncontrollably. So if VD is very large, right, if you apply the VD in a very large amount, this implies the depletion region of drain, right, gets extended till this S region or the source, right. When this happens, right, it causes a huge current to flow, right. This current is actually irrespective of the VGS. Okay, this whole condition is what is called as the punch through effect, right. When this happens, the higher voltage will cause the device to break down. That's a problem here. And also you will see that the thin oxide layer, right, will actually, you will see a arcing over there, right, because of a melt, or you may see a spark over there. Something might happen, right. The next concept that comes under this is called as the MOS models. This is where we are going to look at the DC characteristics, right, as well. The MOS devices are modeled using what type of signals that you are going to apply to that device, right. For example, the first one we are going to study here is called as the small signal model. This indicates that the signal which you are applying to the gate of the MOSFET is small, in the sense very small amplitude, and variation is also very small. Okay, it can be AC, small variation in millivolts, something like that. Okay, so let's write the small signal model directly first. So the small signal model of a MOS transistor is like this. On one side we have a region. This region is the gate. All right. Then between the gate and say the drain region, we have a capacitance being modeled. So this region is what we call as drain. So we'll come to each and every component that we write here. Okay, so this is C, G, D is the standard notation, followed by there is a current source, that is Gm times VGS. Okay, followed by there is another resistance marked here. This is GDS, and we have a capacitance coming here. This is denoted as CDB. Okay, then on the other side we have another capacitance. This is marked as CGS plus CGB. Okay, so this is connected, and this side you have the source. Okay, now see, consider the MOSFET and MOSFET, which we already have discussed. I'll try to give a very brief explanation about this. Right, so between the gate and the drain region of the MOSFET, so consider the original diagram which we had written earlier, maybe a N MOSFET. Is there a connection? Internally, are they connected? Gate and the drain? No, no, don't consider this circuit. I'm asking you to consider the original diagram which we had written, right? They are not connected, correct? So there is no connection. There is no connection because in the middle we have a SiO2 layer which is an insulator, correct? So now the one side of insulator, right, will store either positive or negative charge, correct, depending upon what type of channel it is. On the other side of the SiO2 there will be a different charge getting stored, correct, one side plus, one side negative. So which is the device that stores the charge in this format? It is a capacitor, correct? So that's why the gate and the drain are connected using a capacitor, because there is no connection but there is storage of charges. Right. Same thing is happening. Do you see any connection between gate and the source inside the transistor? But there is a charge storage, correct? That is denoted by two things now. One is the direct gate to source capacitance, that is CGS. C, capacitance between gate and the source. At the same time, there is another capacitance coming into picture, that is between gate and the body, or the, right, the bulk of the transistor. Right, there is also the charge storage, correct? So that's why you can see that, right, there are two capacitance marked over here, right? First capacitance, gate and the drain, we understood. Same thing happening on the other side, right? So two things we understood now. Let's come further, let's go ahead. Right, between the drain and the source, right, it is actually, if you see, the drain and the body is largely storing the charge, correct, because that is reverse biased. Recall the diagram. If you have doubt, let me know, I'll go back and show. Otherwise, I'll quickly go forward. Between the drain and the source, right, drain is on the right side, source is on the left side. Okay, in between that drain and the body, or drain and the substrate, there is a large depletion layer, correct, storing the charge. That charge storage is indicated by CDB, right, drain and the body, or drain out the bulk. Okay, now you see that there is a channel is between what, drain and the source. Channel is made up of uniform material, it acts like a resistance. Previously we just had calculated, in a problem we calculated resistance of the channel, correct? So channel is actually between which two terminals, right? So see the red color mark, that is actually connecting the drain and the source. So that is why the resistance has been modeled over there. And which direction you have a current flow, drain to source, right? When current flows from drain to source, what is the direction of flow of electric charge? It's a source to drain, see the direction. And that current depends on what voltage? It is VGS. See, the current is dependent on that. So everything is modeled right here clearly. That's why this is called as a model. Transistor can be modeled in this fashion. Very straightforward. I hope you are fine with this concept. Okay, so I will just write some of the equations needed, right, so that we can go quickly ahead. Right, there is what is called as a GDS. This is called as output conductance. Some problems we might require this. That's why I'm writing here. So output conductance, that is G drain to source, is equal to the beta value of the transistor into, this is VGS minus VTH minus 2 times VDS. Okay, minus 2 times VDS. This is the GD value, okay, output conductance. Then approximate channel resistance, right? We have another equation. So this is called as linear channel resistance. right? We have another equation compared to what we already have studied. So this is 1 divided by the beta times VGS minus VTH. You can even use this, okay? Then there is another formula to calculate what is called as the transconductance. So transconductance is GM, which you can see in the model. So this is the rate of change of IDS with respect to the VGS, dVds at a constant value of VDS. This is VGS, okay? VGS at VDS being a constant. That's what is this. Okay, right. So these are the different equations which we can use to calculate, right? The different values of corresponding to the transistors. Okay, all right. Now, right, let's go for a problem, right? Based on whatever we have studied in the previous sections, right? So I'll write the question, right? You can note down the important parameters only, okay? If a NMOS has gate oxide thickness of 10 nanometers, gate permittivity 3.9, electron mobility 520 centimeter square per volt second, threshold of 0.7 volts, the W by L ratio of 8, VGS equals to 2 volts, VDS equals to 1.2 volts, then calculate drain current, gate capacitance, okay, gate capacitance. Next, also calculate the drain current if VDS changed to 2 volts. Okay, so this is the question, and this question was a repeated question from old question paper. So Cox is equal to epsilon naught into epsilon, right, insulator whole divided by the D. Nanometers is 10 to the minus 9, but if you want to convert that into centimeter, right, remove two things, two powers from the 10 to the power, so that becomes minus 7. Okay, now you give the value This is 3 point something 45, right? Minus 7, right? This many farads. You can even convert into microfarads. Anyway, that's fine for us. So first part of the answer is done. So in the first case, I understand that the VDS is lesser than VGS minus VTH because of this reason. VDS is 1.2, VGS minus VTH is this. So this means the given MOSFET is in which region? It is in the ohmic region. So in the ohmic region, write the equation for current. In the ohmic region, this current IDS is nothing but this is mu, mobility of electron, C ox, oxide layer, W by L, okay, into VGS minus V threshold into VDS minus VDS square divided by 2. Okay, so let us substitute. So mobility is given, correct? Mobility is given as 520, right? 520 centimeter squared. So I'll write even the centimeter squared. So centi is 10 to the minus 2. Square makes it minus 4. Okay. Cox is 3.452 into 10 to the minus 7. The W by L is directly given as 8 in the problem. Correct? Multiply this with what is the VGS given? VGS is 2. What is VTH? 0.7 into what is VDS? 1.2. Correct? Minus VDS square, that is 1.2 square divided by 2. Substitute these values and calculate the answer. This is equal to 1.20 into minus 7 amperes. Okay, so if you want to make it minus 6, it's right 0.12, right, microamperes. All right, now let's go to the second condition. Check the what are the values of VGS, VDS and V threshold. So in the second case, the VGS is still at 2 because they are not changing that, but VDS is also changed to 2, and we know that V threshold is 0.7. So VGS minus VTH is equal to 1.3. This value is less than VDS, which is equal to 2. This means what? VDS is bigger than VGS minus V threshold. So this implies which region? Yes, it is saturation. In saturation region, can you give me the equation of the drain current? IDS equal to, right, this is mu and C ox W by 2L into this is VGS minus V threshold whole square, correct? Mu n is given, so that is 520 into 10 to the minus 4 into 3.45 into 10 to the minus 7 into 8 by 2 into 2 minus 0.7 whole square. Substitute and get the answer. Kindly repeat. 0.212 into 10 to the minus 7. So you can see that this value is bigger than the previous value. So we can say that yes, current has been increased, and right, this is a possible answer. All right. We are expecting a bigger value than the previous case. Saturation current is more than the ohmic region current. Are you okay? Then, yes, that is correct. Now, I'll give another question, and this question is again from another paper. So, if NMOS device gate thickness of 12 nanometers, epsilon IMS equal to 4.3, mu n equal to 540 centimeter square per volt second, VTH equal to 0.9 volts, VGS equals to 3.5 volts, VDS is equal to 2.1 volts. Calculate Cox and IDS. The solution goes pretty much similar to the previous answers. Okay, please solve it.